I hope all the channels can see my screen, I believe. Okay, if all of you can see my screen, let me go ahead and start the session. Okay, so in this session, what we are gonna see is OpenCV. The OpenCV is an open source computer vision package that you can make use of in starting with deep learning and computer vision path. So I believe most of you would have heard or learned what is machine learning. But in this session, we would be talking about deep learning, which is another domain altogether from machine learning, where you would know how to perform complicated models which would predict or analyze the data set that you provide. And we are going to make use of this OpenCV package to achieve this. And first things first, what is open source? An open source is nothing but an open license software which anyone can make use of without any restrictions within itself. So that's why we chose to go with open source, because you won't have to buy your software, you won't have to buy this particular package to make use of. So it'll be easier for you to start learning or start getting into the machine learning altogether. And we will also discuss about what is computer vision. So what are you trying to achieve from computer vision? Okay, so deep learning. What is deep learning and where does it come from? Deep learning is basically an AI function, and all you're trying to do is you're trying to replicate or trying to reproduce what your brain does. So your brain has the ability to analyze and come up with results which are more complicated for a computer to start with. So you're trying to make your computer or your system intelligent enough to analyze the data, to view the data, or to get the information out of the data or get valid information out of the data, so that you can make use of those results into much more solving much more complicated problems. Okay, first things first, deep learning is nothing but a subset of what machine learning is. So what is the difference between machine learning? So in a machine learning, the data that you have is usually labeled data. So what do you mean by labeled data? Is the data set. So when I say data set, let's say it is a collection of images, or it is a collection of an Excel, or a collection of population information. So those information that you can clarify, okay, so this belongs to a specific animal. This image belongs to a specific animal. It's an image of a dog, it's an image of a cat. So those data are labeled data. But in deep learning, you won't get labeled data. Rather than you will be using unlabeled data to make your prediction or analysis or whatnot. Okay, and that's what deep learning is. And this is how it's different from a machine learning perspective. And what else can you do? So you can learn from what your data gives. So let's say you are taking a real-time data. What is real-time data? It's nothing but you keep getting data every now and then. So let's say you have an IoT device set up to capture what is your temperature of the weather. And this is going to keep giving you at a regular interval of what is the temperature of the weather is. And how are you making use of this constant data? So let's say you collect this data for 1 year. So in this 1 year, you would have gotten many thousands of temperature. So making use of this huge collection of data, you are going to try to predict what your weather is going to be. That's what deep learning is all about. So by provided with a set of data, you're going to create a model, and this model is going to do a job of predicting what is the temperature of the weather is going to be in the near future. It could be in the next year, or it could be in the next month, or maybe 6 months from now. It depends. So that's what you can learn from data. Next one would be layered extraction. So let's say a particular data has multiple features. What do you mean by features? So let's take a table. In a table, you will have different columns. It can be name, it can be description, it can be age of a person, it can be where does this person work, whatnot. So for a person or a row with a person's information, there are different features, which is nothing but different columns in the data. So you're going to extract those features from the data, and then you're going to use those features to analyze or to get the results that you want to get. So that is layered extraction. And let's see how it works. Okay, so as I said earlier, it's nothing but you're making use of unlabeled data. So here I can even go ahead and say, okay, I'm going to use a neural network, which basically has several layers, and I'm going to try to imitate how a human brain works in getting the data and analyzing the data and giving back result. So for example, let's say you're seeing something, you're seeing a particular video, or you're seeing a particular image, and as soon as you see the image, you'll know what the image is. Let's say you're seeing an image of a tree. As soon as the image comes up, you'll know that it's a tree. And how does brain let you know that, okay, so this image is a particular image of a tree, and this image is a particular image of a cat? So how do human brain differentiate it is what we are trying to reproduce from our machine. And we are going to use something called neural network. And in this particular neural network, we will be feeding in a number of input, and based on the input fed in, it's gonna replicate the features, and it's gonna cross match those features into something called neural networks, and then it's gonna give you the final output that you need. Okay, so this is cross matching. So what does this neural network even have? So this neural network has something called hidden layers, which will help determine how many complexities do you want this particular model to analyze. Let's say I want to have like a much more complex solution for a problem, then I would be tweaking with my layers in the neural system so that different cross matching happens. And what does this cross matching? Yes, I will talk about it in the next slide. And for now, let's just say there are multiple layers within a neural network. Okay. So there is another type of neural network called deep neural network, which basically is what we just talked about, which has different layers, but it would help us add more features and then try to come up with a multi-featured network, which would help us determine the solution that we need. And finally, labeled data. So in a deep learning environment, you don't usually get labeled information. You always work with unlabeled information, but you can always go in and manually intervene and extract feature from a labeled data. How it would work in a general scenario. Okay, so this image that you see here is basically a simple example of how a neural network would work. So the input layer that you see, the circles in yellow, would have multiple features fed in. So let's say you're going to analyze an patient's information. You can feed in different types of feature of the patient, like what is his age, what is his ethnicity, and did he have any smoking habits or any drinking habits, or how long did he was he taking blood pressure medication, or how long did he have diabetes? So all these are features that you might need when you're trying to solve the problem. So if you're trying to solve a problem related to a particular disease like diabetes, then you might want to know the patient's medical profile, like age, gender, and duration of the medication taken. But you might not need where the person is from, and you might not need, okay, how long did the person work. So those kind of information you can always go there and tweak, and depending on that you can simplify your input layer. Okay, and based on what input you're trying to give, you will decide as a data engineer, or as a machine learning engineer, you will decide, okay, so for this particular model, it is enough for me to stick to these number of hidden layers, and these number of cross matching is enough for me to get like a rich solution from the output layer. So just because you have 20 hidden layer doesn't mean you're gonna get the right results. So it is more like an intuition rather than how would you say, like the actual result itself. So more is not always better. Here you would tweak with your number of layers in multiple ways, and decide and fixate yourself on, okay, so this number of layers, if I add it to my model, would give me an appropriate or an optimum results. So this is how you can tweak in your neural network, and this is how you can help predict or analyze the data that you have. Okay, so that is the concept of deep learning in itself. And what is computer vision? So computer vision is nothing but when you see something, like I said earlier, you know what you're trying to see. But when a computer sees an image, the computer is not going to see the image itself. Rather, you're going to feed in the byte data of the image into the computer. So how would the computer know what kind of an image it is? And how would you let the computer know, okay, so this is an image of a tree, learn it. And then when I give you an image without label or without telling you what it is, you need to tell me that this image is an image of a tree, is what I expect out of a computer. So that domain which works by letting the computer see and analyze an image or video or what kind of data that you want to feed in is handles computer vision domain. Okay, so in a system that you want to have your model trained in computer vision domain, you need several steps. What is that? Acquisition. So you need to get this data first. So let's say you want the data of a forest, and you want to know, like, in this forest, this particular tree species are more prevalent and this particular tree species are less prevalent. So you want to differentiate that. So, but in order to do this, you need to have the data though. It can be data, or it can be a photo, or it can be a video, or it can be a real-time information that flows in. It can be a real-time traffic information, whatnot. So the first step handles with the acquisition of the data. Second step would be training. Okay, so I have the data now, but the model doesn't know what is what. I need to make the model understand. Let's say, so this is an image of a tree. This is a car. This is a biker who rides a motorbike, and this particular biker is going over the speed limit. So those kind of things I need to train the model. The model by itself, it won't know. So you're going to train the model to analyze and tell you that, okay, so I know the difference between this and this. So that is the training phase. Then comes the processing phase. So you have trained your model, and your model would now be able to differentiate between the things that you want the model to differentiate between. Now, all you have to do is you have to make sure that the model can be automated in such a way that, let's say, you are going to implement a model which would determine a particular person who rides a vehicle. Let's say that it can be car, it can be a motorbike, it can be a lorry, a truck, whatnot. Whether the particular vehicle is going over the speed limit or not. This is what you're going to analyze. And you will be getting real-time feed from videos. So you have a model which is trained to determine this, but you cannot go to each and every input that comes in. So let's say there are about 10,000 signal lights in your area, and you have 10,000 different inputs coming into you. You cannot go and load all those 10,000 videos manually and make the model do your analysis. So what you're going to do is you're going to do something called automation. So automation, it's nothing but you make a system which will make use of the model to determine, okay, so this particular vehicle with this number is going over the speed limit or not. It's like total hands off. You are not touching the system at any time unless if something goes wrong. So this is the processing phase. And finally, you would have an understanding phase. So what do you mean by understanding? So, okay, so in a particular area, or let's say in an area of 10 to 15 kilometer, these many lights have most overspeeding, and these many lights have the least overspeeding. So what you can do, so this is the information that you gathered from your model. So how are you making use of this information in a real life scenario? Okay, so if this is the case, if this is the area where so many people are overspeeding or they are violating the lights, then you assign more cops in this particular location, and you can make sure less cops are assigned in this particular location. So this is how we can make use of this model and provide a solution for a real-time scenario. So from this, you would know that computer vision is nothing but, as a human, you would get a high-level understanding from watching an image or watching a video. But how would you help, or how would you make use of a computer to do the same job in real time, and it can handle multiple input sources to achieve a greater purpose, is what this domain is all about. Okay, now I'm going to talk about what an OpenCV is. So this is, OpenCV is nothing but a library. Okay, so library in the sense, there are so many algorithms which is written into this particular package, and all you can do is you can adopt those methods as an which already has the algorithm pre-implemented, and you can work on solving the problem rather than coming up with the algorithm and coming up with the best case scenario for the algorithm and going too much technical into it. So let's say you have a problem to solve, and how like, let's say for an example, I need to find out so what kind of trees are there in a particular forest near my area. So this is my problem, and I need to solve it. If all I'm trying to focus on is solving the problem, I cannot spend time in coming up with an algorithm to solve the problem. But if I'm doing a research on this particular algorithm, yes, I will spend time in coming up with the real-time algorithm which has best results. But that won't be the case when I'm trying to solve on a real-life problem. So all I would try to do is, okay, there should be an algorithm already, and I should just choose between which algorithm I'm going to choose to solve my problem. That is all I'm focused on. So OpenCV, it was founded in order to provide a powerful and reliable infrastructure, which as a machine learning engineer or a data science engineer, you can build upon. And it makes available of many useful algorithms out there, which can be made use of in solving your machine learning problem. And this was originated in Intel in the year 1999. And from the year 1999, it's been made available for public use, and it's been supported by lots of uh, great machine learning developers and in building upon this particular OpenCV platform. And as I said earlier, since this is open source, it is free and it can be used for research purposes. And as far as license goes, it is licensed under BSD and it supports Linux, Windows, Mac OS. So it doesn't matter which kind of a system that you use, you can always adopt this library and you can make use of it. Okay, so I was talking a lot about OpenCV, but from this point onwards, I'm going to go into more technical, where what kind of functionalities is this OpenCV offering you that you can make use of. So think of it more like I'm not telling you, okay, you need to use all these functionalities in OpenCV to learn it. No. So in order to get introduced into the field of machine learning, think of it this way. Find a problem first, and then based on the problem, see what can be made use of from the available functionalities. So if you see the OpenCV library, there are over 500 functionalities that has been given to you. You don't have to use all of them, but what do you really need? That's what you need to find out. For now, let me tell you what are all the functionalities that are there, so you can make the choice of using which one to use. Image processing. So let's say you want to create an image itself, or you want to display a particular image in your system, or basically you want to process some image. If that is what you're trying to achieve, then you have pre-developed methods available in OpenCV to make use of in the library. So let's say all you want to do is, okay, so I want to feed in an image and I want the model to start analyzing it. So all you need is like 2 or 3 lines of code, and then boom, you have that functionality there. You don't have to write like 100 lines of code for just processing an image. So that's the main advantage. Next one, segmentation. So what is segmentation? Segmentation is nothing but breaking down any object based on the functionalities that you need. So here, since we are talking about image, it's basically like I'm going to segregate this image into different levels. So let's say I'm only focused on the color of the image. So let's say I want to detect a tree from any other object. What does a tree have in common? Most of the trees have brown trunks and green leaves. So that is what I'm looking for. If an image has more of a greenish or a little of brownish tint to it, then I can assume that this particular image is an image of a tree. And if it is of any other tints, any other color tints, then I can assume that it might be something other than a tree. So that is segmentation. So you can break down based on the RGB ratio, and you can make use of those values, and you can say, okay, so if it has this much amount of green and this much amount of brown, then I can assume that, okay, so this is a tree. So that is segmentation. Next one would be transformation. So let's say you have, if you've ever taken a photograph from a digital camera or from your phone or whatnot, you would always know what is called as blur. So if you want to, have like a clearer image, you would need to transform your image, or you need to work with that image to basically edit it. Let's say if the image that you got was not bright enough, you might want to brighten it up a bit and make use of that particular image. So those kind of transformation that you need may be perspective, warp, or scaling. So let's say you have thousands of images, and 80% of the image has 500 by 500 pixel, but 20% of the image has 250 by 250 pixel. You cannot use the image directly because you need all the image to be of the same size so that your result is optimal. So in that case, you'll have to scale the image up to 500 by 500. So those kind of operations, you can just do it in like a single line of code. You don't have to spend a lot of time coming up with, okay, how am I going to scale these many images? and how many lines of code should I write for this particular problem. So this is like click and you're done. Then machine learning. So in order to solve a particular problem or machine learning problem, you can implement any kind of algorithms. So in this case, I have mentioned like Bayes algorithm, k-nearest algorithm, SVM, and whatnot. There are so many different algorithms out there. Based on the kind of the machine learning problem that you're trying to work with, you can choose an appropriate algorithm. And as soon as you choose the algorithm, okay, so this is the algorithm that I'm going to go with, and you go through a strainful process of coming up with the implementation for the algorithm and coming up with the complexity or time complexity, space complexity, and whatnot, and doing all those work can be avoided in this particular functionality, because here in OpenCV you have all those algorithms made available for you, and all you have to do is, okay, so I'm going to use this algorithm in my model and then see what is the result. So okay, so if this particular result is not enough for me, then let me go with another algorithm and see how the result is. So you can always be flexible on what kind of an path you take solving a problem, rather than sticking to one specific solution. You can always compare and contrast different algorithms and see which is giving you the most needed results. Next one, let's say geometric descriptors. Okay, so there is an vehicle that is moving in a video, and you need to find, okay, so this particular vehicle is moving at this speed. This particular vehicle is 10 meters away from the camera, or 5 meters away from the camera. So those kind of calculations that you need to perform is made available to you directly, and based on that you can determine, okay, so this particular person who is standing in front of the camera is 6 feet away, 10 feet away, and whatnot. Next, tracking. So tracking is nothing but, let's say, like I said earlier, you're trying to solve a particular vehicle is going over the speed limit, and how would you know how many vehicles are there? How would you know what kind of speed it is going? How would you determine, okay, so this is a truck and this is a motorcycle, and how would you know for a truck this is where the number plate is, and for a motor vehicle this is where the number plate is, and for a car this is where the number plate is, and where should I look for those number plate? So all this comes under tracking. So you need to know that there is an object first, and once you know an object is there, then you'll determine what kind of an object it is, then you'll determine where to look for, and then you determine what the data is. So that is the number of features that you'll have to incorporate. So the first step for that would be tracking, and that is also provided to you within this package. And finally, I would say fitting. So fitting is nothing but you just work with morphological transformation, like erosion of a particular image, or like dilation of a particular feature. So this is the feature that you don't want. Let's say you have a tree which is like super green, and you don't want that much green in your image. You can always dilate that particular feature and whatnot. Camera calibration. So a main thing that you'll have to know once you start working with a real-time device is you can't use the data as is, because the data that is provided to you directly in a raw input would not be able to be used as is by your model. So you might have to work on calibrating your camera or calibrating your model to work with the input that you get, or modify the input that you get. So all these you'll have to end up working with a distortion matrix, or like a camera matrix, or reprojection values to adjust your input. So these kinds of intrinsic calibration can be done from this library. So these are some of like little bit of features that is being given by OpenCV, but it is like a huge library with lots of other features you can always work with, or tweak with, or play with, or whatnot. So as I said earlier, it is basically in a computer vision domain, OpenCV stands out like a beacon, where as a student or as a researcher, you can just jump into this library and make use of all those wonderful functionalities that's been given to you. Okay, next. When I give you two images, the one on the left and the one on the right, what do you see? What do you understand? Now, I want my system to see and understand these images too. And why I need this system to be able to understand these images is because I'm trying to solve a higher purpose, or I'm trying to make something out of the understanding that the computer has. Maybe if you are able to get your computer to understand something that you as a single person can understand, you can make your computer to understand something that a whole group of people can understand. So think about the achievement that you can reach by having multiple brains working on the same problem. So your resolution time is gonna drop like crazy, and you're gonna get the result you need in a much faster time. Okay. So that is what we are going to try to do. So we are just trying to do some detection or enhancement techniques that using OpenCV in this computer vision domain. Okay. First things first, deconvolution. Like I said earlier, whenever you take a moving object, or like whenever you take an image while you are moving, it might always have like blurs in it. So let's say you go online today, you go to the Google data sets that's there, that's available there, and you try to download a data set of 1 GB with multiple images in it, and you're trying to work with these images. There is no guarantee that all the images that is given in this data set is going to be pristine. There can be images that is blurred. There can be images that is not of the size that you need. There can be images that doesn't even look like the image that you have. It can be the image might look like a car to you, but a computer would have no idea that it's a car because it's blurred. So in this image itself, that the one at the top and the one at the bottom, as a human, you would know that okay, the one at the top is basically a billboard, and the one at the bottom is basically a biker who's trying to ride his bike. But how would you let the computer know? You need a much more clearer image for the computer to understand that, okay, yeah, so this has clear features where there is a handlebar, where there is a wheel, where there is a headlight, and where there is a post, and it has letters on it to determine what object it is. But when you feed in an image like this, you're basically making your model to predict wrong results. So you need to tweak with your images and make sure that whatever image that you feed in is of pristine quality. Even if it's not of pristine quality, it's of like an acceptable quality. So for blurs, we are going to use something called deconvolution, where you can restore an image and remove the motion blur from the image. So if you see here, compared with the earlier image, this is much more visible or much more clearer in terms of an system. So even for you, if you see in the previous image, you would never have be able to read what those letters were, maybe a little bit here and there. But as you can see in this one, this image, this is like much more clearer than what it was. Same thing goes for the biker too. It has much more definitive structure to the bike as well as the person on the bike, rather than having like a blurred image of guessing what the definitive structures are. So that is deconvolution. You can make use of a deconvolution feature that is provided by the OpenCV to reduce particular motion blur. So why am I talking about these features? Why won't I go to a specific problem and try to solve this? My intention here is I'm just giving you an overview on what is out there. And you need to find out, okay, so this is the problem I'm going to solve. So this is the problem that I like to be solved. So when I try to solve with a problem, I need to know what are the stuff out there in the market or out there in the world, so that I can make use of those features and start working on them. So that is my intention here. And that is why I'm going over the features rather than choosing a particular problem and trying to solve it. Okay, bounding boxes. So let's say you are trying to pinpoint a particular object. So in this case, it is face detection. and you have your IoT device setup. It has a camera module, and all you're trying to do is like you're trying to, as you would have seen a lot of videos where people would be trying to, based on the face, they would try to determine the age of the person, and based on the video they would determine, okay, so this person is a male, this person is a female, and whatnot. So when you're trying to solve a problem like this one, the good sign here would be, if your implementation of the code works, you would see multiple bounding boxes over your object. As soon as you see this, you can be happy that, okay, your implementation works. Now all you have to do is suppress those multiple detections, or detecting the same object again and again. So here you can make use of something called non-maximum suppression, where you suppress the multiple detection of the same object. As you can see here, the guy and the girl has multiple boxes over their faces, detecting that, okay, so this is a face, 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 face. So you're trying to suppress those multiple boxes over each person's face, and in the end, you only should have one box per face. And the area where a box is available for them holding hands is a non-responsive or a spurious response. Okay, so you need to suppress those spurious responses as well, which is basically, is not a face, but rather the model is assuming that, okay, so this might be a face because it is not clear enough, and those responses should also be suppressed. So here you can make use of a non-maximum suppression feature that is provided by your OpenCV to say that, okay, so this is an actual face, and the other bounding boxes are basically gone, and even the spurious response is basically gone. Okay, in the next stage, what I'm trying to do here is I'm trying to detect Parkinson's disease with computer vision using something called spiral test and a wave test. This is the problem that I'm trying to solve. I need to know, okay, when given a data set and I have a problem, I need to see how many people from the data set has Parkinson's disease, yes or no. That is all I need. I give you like 100 images. Okay, so out of these 100 images, you're going to feed these images into this model, and the model should say, okay, so out of these 100 images, 20 people have Parkinson's disease, 80 people does not have Parkinson's disease. That is all I expect. So this is what you're trying to do. So how would you start solving a problem this way? First, what are you trying to solve? So here, Parkinson's disease is nothing but a disorder of the central nervous system that basically impact how you would move. Let's say it can be moving your hands or walking around or whatnot. So they won't be able to do in the same way as normal people can. So all you're trying to do is you're trying to predict, okay, so this particular person might have Parkinson's disease, yes or no. Okay. And now, how are you going to do that? So you know what it is. So how are you going to do that? So there has been a study that you can say that a person has Parkinson's or not by asking them to draw spirals and to draw waves. I'll show you how it looks. So you're trying to ask a list of patients, let's say 100 patients, and you're trying to ask them, okay, can you please draw a spiral, and can you please draw a wave? So based on what they draw, we are going to analyze those waves and see if there are any distortion in those images to check whether this particular person might or might not have Parkinson's disease. So this is a research study that is made, and we are going to make use of this research study by implementing a model to decide the result. So this is how we can, you don't have to go there and make the research and then do it, but rather you can make use of any research that has already been done and already been verified, and all you're trying to do is you're coming up with a software that basically does what the research says would be the right way to do it. So this is the how part. And the final part would be why. Why are you even trying to solve this problem? That is the next stage. Uh, so here, let's say that if I can detect that a specific patient has muscle tremors. By muscle tremors, I mean shake in when they try to write. Then it means that there is a chance that this person has Parkinson's disease, right? So instead of making a person go through a strenuous amount of tests and diagnosis and whatnot, and finally coming up with saying, okay, so this person might have Parkinson's disease, or with the medical test, you'll know, yes, this person has Parkinson's disease, or this person does not have Parkinson's disease. But that would not mean you would ask all the 100 people to take this medical test, right? Because it is expensive and it takes a lot of time. And by letting people who doesn't have Parkinson's take the Parkinson's test is basically waste of the resource that is being offered. So this, all you're trying to do is, okay, I'm coming up with a model to know, okay, so these persons are eligible to take the tests, and these persons, they don't have any problem, so they don't have to take the test. So that is how I'm trying to solve here. So this is the why part. Okay, and now this is how your wave looks. So you basically give them a set of dots, and you basically ask the patient to connect those dots and draw a wave. A person without Parkinson's disease would be able to do it in a GIF, but a person who might have an onset of Parkinson's disease, you might see that there are tremors and those lines would not be proper. So this is a study that was conducted in 2017 by Zam et al. And he determined that this is the way that you can show that this particular patient has onset of a Parkinson's disease or not. And this is the study we could make use of to solving this problem. Okay, so what kind of a data set that we have? So you cannot like just go there and start working on it, right? You cannot go to unless you're researching on this particular topic. You cannot go to a hospital and get this data from a patient. So what you can do is like this data set that I have is obtained from NIATS. It is an university in Brazil, and they have done the test and they have verified that, okay, so these many patients we've analyzed, and they did the medical side of tests. So all we are doing is we are doing the software side of tests. So in this particular image set, they had worked with 102 patients and got the patient to draw 102 spirals and 102 waves, and this is what we are going to use. So, and this one I'm splitting it into testing and training. Why am I splitting it into testing and training? So the majority of the data set that I picked for training is to train the model. So I need the model to know that, okay, so I'm gonna give the 72 images from spiral and 72 images from wave into the model by saying that, okay, see, this image has Parkinson's, this image does not have Parkinson's. I'm gonna make sure that the model knows the difference between a Parkinson's onset patient and this is the image of a non-Parkinson onset patient. And then once the model is trained, I'm gonna try it out with the testing data set that I have and see, okay, so out of these 30 images, how many images is my model predicting right? How many images is my model predicting wrong? So this is why I split the data set into two, and then I'm trying to work with that. Okay, so this is how the image would look like. So the spiral images would have basically the spirals being drawn on, and from this you can see that the ones on the left has no tremored in the image, but ones on the right has severe tremors. And the same thing goes for the wave as well. The ones on the left doesn't have much of tremors, but ones on the right has most tremors in the images. Okay. In order to set up an environment where you can test out the implementation, you might need these packages to work effectively. It's not that for all the problem you need all these packages. Depends on what kind of an approach you take. You might make use of these packages. First thing first, the one that we are discussing about OpenCV. So in order to install OpenCV in your local, you just have to do pip install OpenCV contrib Python, and this would install the package into your Python environment. Then you would need pip install numpy. So numpy is nothing but you just end up performing numerical uh, tasks, and imutils is basically like an utility package when you're working with images. Scikit-image is also an utility package, but more of an research oriented package. And there is also one more, scikit-learn is basically helping you work with machine learning utilities. So these are some of the packages that you might need when you're trying to work with a machine learning problem. And you are using images. So in this case, we are using images. But if you're not using images, you're using like a text data, you might need different kind of packages to work with. Okay. So the main thing when you try to work with the results from the model. Okay, so you fed in the data, the model is predicting, and you have the predictions from the model. So how would I know this prediction is making use of at all? Or even if it's right, or even if it's wrong, how does it make sense? That's where specificity and sensitivity comes into picture. So here I'm trying to work with a medicinal problem where you're trying to predict a particular patient has a disease or not. Whenever you're trying with a medicine domain, it is okay for your model to say, okay, this patient doesn't have Parkinson's disease, but it is totally fine for the model to say, okay, this person has Parkinson's disease when he actually does not. That is acceptable. Okay, but it is not okay for a model to say this person does not have Parkinson's disease when the person actually does. That is in no way acceptable, because you are basically denying a patient with active disease onset, and that would not be a right way to use this model. So when you're tuning based on, so that is what specificity and sensitivity is. So it is specificity is true negative when it is basically the actual medicinal result is negative, but your model is saying it is true. And sensitivity is nothing but the actual medicinal result is positive and your model is saying it's false. Okay, so you can have low specificity, but you should always have high sensitivity as much as you can. So in a naive approach, a model would have 86% specificity and 76% sensitivity. So here, since 86% is a good number, you can ignore or you can leave the specificity as is. But 76% is not a good number when it comes to sensitivity. So you need to work on how can you improve your model to have higher sensitivity. And there are several ways that you can work with, which would involve like much more knowledge into what your model actually is and where can you tweak it and whatnot, and then improve your sensitivity. Okay, so these are the resources that was helpful to me in coming up with this approach. So you can always go to this opencv.org and see what kind of features that are coming in or what kind of features that were made available already and whatnot. So that is OpenCV Vision Library URL. And if you want, you can make a note of these URL as well. And the next one will be PyImage search. So PyImageSearch.com is run by an professor called Adrian Rosbrock, and he gives out many useful information regarding different types of models, be it for a naive person or be it for an experienced person, to just try out and work with and get to know of the recent advancements in machine learning world. And then finally, since I was working with Parkinson's disease, I had to go through the other 3 links, which you can take a look at it, but it is purely optional for you to go into and take a look at it. So these are the resources that was helpful to me, and I believe that it would be helpful to you too when you're trying to work with machine learning problems. And this is me, Rakesh Ramakrishnan, and as introduced earlier, I work as a developer at SAP. So if you have any questions, feel free to ask me now, or you can always reach out to me in any other channel that you feel, or you can always reach out to your professors, who can in turn reach out to me to convey your question and get the answers that you need. Any questions so far? Okay. So I assume that from your silence, either you don't have any questions, but in the future, if you do have one, please feel free to reach out to me. Thank you so much.
Thank you, sir. I'm Indira Salil Bharti from second year CSC department, here to give a vote of thanks. First of all, I would like to thank our Almighty God for making today's event a success. I would like to thank our Honorable Principal, Dr. John Oral Bhaskar, and our Director, Mr. Amrit Raj, and our HOD, Dr. Julie Josephine Ma'am, for organizing such an event for us. I would like to thank our guest, Mr. Rakesh Ramakrishnan sir, for such a wonderful sessions. We got to know about machine learning and computer visions and many more topics on that, which would be helpful in our future. I would also like to thank our faculties and resource person for their help. Last but not the least, I would like to thank all the students who attended this seminar, without which this session wouldn't have been succeeded. Thank you.
Thank you, Indira. So you all can go for the break and join for the next session in another 10 minutes.